Welcome. I'm going to just do one more video on gravitational forces and gravitational potential energies. And in this video, I'm trying to show you how the general case, this is the universal law of gravity, how that turns into the specific case when you're near Earth. You should be able to go from the general to the specific and show how that turns into that. So I'm gonna detail that for you. The first one is very simple. If I'm near the Earth's surface and I have a mass m1, and I do take this equation, the force of gravity is equal to the negative g m1 times the mass of the Earth all over the distance between them squared, which is the radius of the Earth squared. Put a unit vector there. That unit vector is a magnitude of 1. Its direction is radially outward, and since there's a negative here, this really is saying that the force of gravity is going to be radially inward because of the negative. Okay, if I just move the m1 out of there, pull it out and put it in front, oops, I moved this m1 out, that's gone. Then, and I need a unit vector there. Then you'll see that the thing in the parentheses is lowercase g. That's the acceleration due to gravity. So that just turns into m1 times g, since this is lowercase g. The acceleration due to gravity, or the gravitational field strength, sometimes we call that. Okay, so that one was pretty simple. Now what I'd like to show you is for potential energy, we should be able to go from the general form for potential energy to the specific form. Now a couple things about the specific form. This is really the change in potential energy. And when you use this, the g is really the absolute value of g. You're not using the vector of it. It's just mgh, where g is 9.8 meters per second squared. You don't put in the negative for g. All right, so let's get going on this. I'm going to take a mass, and I'm going to move it up a height h. And from last year, you know that this, compared to this position, this has a potential energy, you called it PE last year, of mgh, where g was not a negative, but just a positive value. I want to show you that we can get mgh from our more general equation. So this is how it works. It's a little longer, but I want to show you that it works. Okay, so delta U is going to be the potential energy it has when it's at a height h, so that would be negative g, mass of 1, mass of the Earth, divided by its distance from the center of the Earth, so that would be Re plus h, minus the potential energy it had when it was at the surface of the Earth, so that would be negative g m1, mass of the Earth, all over Re. So there it is. It's U final minus U initial. This is U final. This is U initial. Okay, let me, since that's a positive value right there, I'm going to put the positive value first. And I'm also going to pull the G M1 ME out of each term. So I'm left with G M1 ME. I'm going to bring this out in front. So it's going to be 1 over Re minus 1 over Re plus h. Okay, I'm going to combine these terms, so I'm going to get a common denominator. Get a common denominator, maybe I'll do Re times Re plus h. That's going to give me Re plus h. up on that one, then minus, and then this one's going to be RE times RE plus H. And that's going to give me RE. Okay, well the RE's cancel, so the RE's will both cancel, and so this turns into G M1 mass of the Earth, and I'm going to just have, when I subtract these, the RE's will cancel, and I'm just going to be left with an H on top, and then underneath I'm going to have RE times RE plus H. Now, if H is much, much smaller than the radius of the Earth, and in the problems that you did last year, it was, you were lifting things 1 meter, 2 meters, 3 meters, and the radius of the Earth is, you know, like 6 million meters. And so when H is much, much less than RE, then this is going to go to, when you add H to RE, you basically just get RE again. And so this is going to turn into G M1 ME H, and this will basically be RE squared. Okay, well, do you see a G in here? G is just capital G ME over RE squared. So if I do that, then I basically have M1, and this is G, the absolute value of G, really. Let me put the absolute value sign in there. So that'd be G ME over RE squared times H. So it's M1GH. Hey, last year when you were doing that, did you know that was an approximation? That was just an approximation, but it's a very, very good approximation. As long as the radius of the Earth is much greater than the height that you're lifting it. So in both instances, I showed how the general equation gives you the simpler equation when you're near the surface of the Earth. Hope you followed that. All right. See you in class.